The objective of Lab 9 was to create a model that accurately predicted the motion of a spring oscillating in 2 dimensions based on a video of that spring. And my main result was that my model was pretty accurate. The only inconsistencies are due to the fact that the spring has sensitivity to initial conditions. Here are the initial conditions for my model. You can see them in the top right corner of the screen in the blue box. I was given the mass of the ball. I found the initial position using tracker data, and the initial velocity is 0 because it was dropped from rest. I calculated the spring constant and the relaxed length of the spring from the video, the first video where the spring moved in 1 dimension, and it was given that this is the same spring. The spring constant was calculated using the oscillation period, which is the first formula under the box, and the relaxed length of the spring was calculated using the force of the spring formula, the second formula under the box. And we knew that at equilibrium, the force of the spring equaled the force of gravity. I knew K and I knew L, so I could solve for L naught. Here's how I went about predicting the motion of the spring and the mass. I used the formulas you can see in the boxes. The blue box shows the formulas for the spring force, which I used in calculating the momentum because I use a momentum principle, which includes a net force, and for this system, the net force would be the force of gravity and the force of the spring. And in the red box, you can see all the updated momentum principle, so showing how to calculate the velocity, the momentum, and the position. I also created a ball that showed the real motion of the ball and spring, and I just did this by importing the position data that I got from analyzing the video and tracker, and just made the ball follow those data points. And this process can be seen at the very bottom of the screen. Here I recorded the oscillation periods for both the observed and predicted motion in the x direction, and how I did this was I looked at this graph, which was made on Python, and I used the cursor to scroll over to the second top peak. I recorded the time, and then I went to the first one and recorded the time, and I did the second time minus the first time to find the oscillation period, because it is the time it takes to get to the same point on a second wave. And as you can see, my observed and my predicted oscillation periods are the same. Using the same technique I used to find the oscillation period in the x direction, I found the oscillation periods in the y direction, and these two are very similar but not exactly the same. The observed is 1.55 and the predicted is 1.62. When rounded to the nearest tenth, that they're both 1.6, so they are very close, but not exactly the same, and this of course is due to the sensitivity to initial conditions. Here's how I calculated the energies. I calculated kinetic energy, potential gravitational, and potential spring energy, and I did this just by using the formulas, for which you can see in the green box, and you can see in the code on the screen. Here's a graph I created in Python. The red line is the change in total energy, and the green line is the change in spring potential energy. As you can see, the change in total energy is always 0. This makes sense because all forces acting are included in this system. In the previous lab, we said that the spring was outside the system, so it was having some external work done on the system, so the change in total energy was not 0. However, when the spring is included in the system, the change in total energy is always 0 because the spring is spring potential energy. And as you can see, the spring potential energy follows an oscillating pattern, just like the spring does itself, and this is true for all the energies included in the system. They all follow an oscillatory pattern, and this is because the spring follows an oscillatory pattern. So I explained the oscillation periods in the x and y positions, and why are they different? Because they are different. And they're different because there might have not been the same amount of stretch in the x and y direction. And this would lead to different energies, because with more stretches, more energy, and vice versa. And this would result in a different frequency between the two, because more energy would mean higher frequency, so that if they had different energies, they would have different frequencies. And this would lead to different periods, because the period of oscillation is 1 over the frequency. So the second question, determine the work done by the surroundings in my new system. And is the energy principle satisfied? And yes, it is. And I talked about this on the previous slide, that work is 0 because the change in energy is 0. And this all makes sense because the forces acting on the system are all internal, they're no external, so there should be no work done by the surroundings. So for the third question, changing the location of the origin, how would that change the physics? It wouldn't change the physics. It would only change the individual numbers. And because when we are looking at the velocity, the momentum, the energy, and all these things, we're looking at changes in position and changes in velocity and all of that, it wouldn't change the actual motion. It would only change where the motion occurred. So while the final and initial positions of the mass would be different, none of the other things would be different.